Thank you. It's a pleasure to be with you all. Actually, this is my second visit to the school. The first one was just right before the pandemic began about 2 years ago. So on both sides of the pandemic. So what I'll do is I'll talk to you a bit about just different aspects of the astronomy that we do, a little bit about the observatory itself, and then some of the research that I do, and just the last part, how fun astronomy is and fascinating and captivating, all these things. So yes, as Mr. Harvey said, I'm both a priest, a Catholic priest, but also a scientist. And so let me talk a bit about the observatory first. Most people are very often surprised that the Vatican would actually administer, sponsor an observatory, which it has for the last 500 years. And so when people find out that there are a number of priests and religious brothers who work for the observatory who are also scientists, they're very puzzled because most people as Mr. Harvey said, think that the world of religion and the world of science are completely incompatible, two different types of mutually exclusive domains right there. And so people think of Galileo right away, or Darwin, and those types of battles as well. But most of the history of certainly the church has witnessed a wonderful overlap between science and religion. And in fact, the church has been a very important contributor to the sciences for most of its history. The person who came up with the theory for the Big Bang, right? The Big Bang, the origin of the universe, the Big Bang theory actually was a Catholic priest, Father Georges Lemaitre, a contemporary of Einstein a couple of decades ago. So there's a lot of overlap. And so yes, the Vatican Observatory is run by the Vatican. And of course, for all of us who live here in Rome, we know where the Vatican is. And of course, you know that it's the home of the Pope and where the church, the Catholic Church, is administered and all these things. So you see Pope Francis there and Pope Benedict. There you have a map of Vatican City-State. And of course, you can see St. Peter's Square and the Basilica. But if you look at the big rectangular building that points up, what are now known as the Vatican Museums, right? Actually, in a small tower that you would notice if you're in the Vatican Museums, especially when you go outside to a big courtyard, you'll see a tower that is not remarkable by any means, but that's actually where the observatory was founded. And so if you look at the upper left-hand corner, that's the Tower of the Winds. And it's inside of there where the first work of the Vatican Observatory was done. It was founded in 1582 by Pope Gregory XIII. And for a very practical reason, as Mr. Harvey said, astronomy has always been very important to humanity, and so much of the motions of the heavenly bodies has been connected to our own rhythms right here on Earth, right? When to do the harvest and all these things. And so what happened is that the observatory was actually founded for a very practical reason. It was a well-known fact by the 1500s AD that the calendar that had been in use for 1500 years, approximately, the Julian calendar, was already not giving accurate results. It was about 2 weeks off. So when the calendar predicted the advent of the equinox, right? The spring equinox, for example, which will be next week, by the way, when we go into spring. That prediction was very different from the actual equinox astronomically. And so, I don't know about you, but you know what will happen to you if you are even 5 or 10 minutes late to class, right? Or to work as well. Imagine arriving to class 2 weeks later, late, and saying, well, I was just only following the calendar. Of course, you'll probably get detention, or if you work, you'll have a job, you'll be fired. So of course, it was recognized that the old calendar needed to be reformed, and that was the very first work, an important part of the Vatican Observatory's work in 1582. And the calendar was named after Pope Gregory, which is why it's called the Gregorian calendar, the calendar that we still use today. And we needed astronomy because, well, a lot of the ways that we tell time are connected to the movements of the celestial objects in the skies, right? A day is measured as what? The amount of time that it takes the Earth to rotate once around its axis, right? 24 hours, or a month connected to the movement of the moon around the Earth, right? Or a year, the movement of the Earth around the sun, right? And so thus you see the need for astronomy with something like that. So the observatory was there in a part of what is now the Vatican Museum for a couple of years. Then it was moved to the top of the Church of St. Ignatius, Sant'Ignazio, which I think many of you have probably been to. It's the church with the fake dome. And so actually the telescopes were on top of Sant'Ignazio. That was the very first university for the Jesuits. Back then it was called the Roman College, or the first Gregorian University. Then in 1870, we lost that. And so the observatory had to be refounded. And so it was refounded inside the Vatican itself, what's left of the Papal States, the Vatican City. So if you look at the picture of St. Peter's, look behind the dome, and you see all those domes along the back wall. Those are all telescopes back there, okay? And so that's where the observatory was located up until roughly 1929. But because of light pollution in Rome, right? It's a big city. The telescopes had to be moved out to Castel Gandolfo, which is where the Pope has his summer residence, right? Because it was much darker there. And so we've been there since then. By the way, this are a couple of pictures of astronomy being done when those scopes were over there in Vatican City, behind St. Peter's Basilica, right over there. And then these are a couple of pictures of lab rooms in the Pope's Apostolic Palace, where science was being done, believe it or not. And then, yes, so if you leave Rome and you go in the direction of the Castelli Romani, which I think all of you know, right? If you go in the direction of Frascati and Rocca di Papa, you go to Castel Gandolfo, Marino, Aricia, Albano. If you look at the lake that's right there, the crater lake, that's where Castel Gandolfo is. And so, of course, that's where the Pope has his summer home, and that's where the observatory continues to be located. So we have two telescopes that are actually on the terrace, the terrazza of the Apostolic Palace there. You can see Crater Lake, Lake Albano, all the way on the right, correct? And the Papal Palace overlooks Lake Albano. And then if you see the picture on the bottom, if you're on a boat on the lake, looking at the Apostolic Palace, you see the domes, two of the telescope domes up there as well. So those two upper pictures are what it looks like inside the Summer Palace. You see one of the telescopes up there on the top left. And if you go into that dome, that's what you see, the refracting telescope, a visuale telescope. The two bottom pictures have to do with our new location for astronomy, because when it came time to build another telescope, because for as nice as these telescopes are that we have in Castel Gandolfo, the problem is age, right? To do modern science, you do need modern instruments. And so by the 1990s, these telescopes, even though they worked very well and are beautiful instruments, they were no longer powerful enough to continue to do modern science. So we needed to build a new telescope, to do a modern telescope. The Vatican gave us permission to do that because the observatory is owned by the Vatican. And so, yes, they gave us permission. But then the other question became, well, do we build the new telescope here in Castel Gandolfo, right outside of Rome? We're about 16 kilometers outside of Rome. And the answer, unfortunately, it was no, because once again, in the roughly 80, 85 years, almost 100 years since we've been out in Castel Gandolfo, Rome has grown a lot, to the point to which we are now a suburb, sobborgo of Rome. And once again, the problem is light pollution. Right? The one thing that you always need if you're doing astronomy from the ground on Earth, you need dark skies. You can have the most advanced telescope in the world, but if you do not have the dark skies, okay, you will not be able to do much. Because of that, we had to build our telescope elsewhere. And in the end, we wound up building our telescope in the state of Arizona, outside of the city of Tucson in the United States. Why there? Because even though there are many locations on Earth, on the surface of the Earth, from which astronomy is done, the four main hubs for astronomy on the ground, okay, we're not including orbiting telescopes like the Hubble telescope, or now the James Webb telescope, right? But telescopes on the ground, there are four big hubs, international locations to do the astronomy. Arizona is one of them, where we are. Hawaii is another one, on Mauna Kea volcano. And then on the Canary Islands, which are Spanish, there is another big center there. And then finally, in Chile, in the Atacama Desert, that's another big center for astronomy, where many countries have built their telescopes, their observatories, to do astronomy there. Okay, so usually you find about 50 telescopes in each one of these hubs. So we were invited to build our new telescope right there outside of Tucson, Arizona. So we are in the desert, and then you go up a mountain, and then you see that. So you see that mountain right there. We are on the very summit of that, and you see a picture on the right. That's the telescope, our modern telescope. As you can see, it looks very different, right, from the older ones in Castel Gandolfo. So these are pictures of our telescopes in Castel Gandolfo here in Rome. They're beautiful instruments. They still work, but unfortunately, they're not as powerful as they need to be. So we have already done most of the research that can be done with them. Occasionally, we can still do a good scientific project with them, so they're not useless. But for the most part, they're not in high demand. Then we go to Tucson, Arizona, into the desert. And so all the way on the top of the mountain, Mount Graham, which is 3,000 meters high, on the summit, there are 3 telescopes that are there, of which one is ours. And so you look on the top left-hand corner, and that's our telescope right there inside the dome. It's a beautiful modern telescope. It's a reflecting telescope, meaning that its main component for collecting the light is a parabolic mirror. Okay? You can see the dome on the outside right there. You can see a picture of where the telescopes are located right there on the top of the mountain. Why build so high? Well, because look at the picture. The clouds are below you. So you'll probably have good, clear skies most of the year. Not always, because it's always possible for higher clouds to pass by, right? Anyway, those are some pictures of life right there at the observatory in Arizona. And then the bottom center one, that's me in Castel Gandolfo, by the way, right there. These are some older pictures of the popes since they're the patrons of the observatory, right? Visiting the observatory. This is here in Rome, Pope Paul VI. You see the bottom picture is where he's actually addressing the astronauts who landed on the moon. So Neil Armstrong, Buzz Aldrin, and I think Michael Collins as well. I mean, so a few select world leaders were invited to speak to the astronauts. The Pope was one of them, Pope Paul VI at the time. Like that. So that happened here in Rome, Castel Gandolfo. We have the popes visiting the observatory. You see the picture of Pope Benedict on the top left-hand corner. He is actually holding a very important rock. We have a very impressive collection of meteorites at the observatory, the Specula Vaticana, which is what it's called here in Italy. And that particular rock that he is holding is actually a meteorite from the planet Mars. So that's a Martian rock. Okay. I've never been allowed to hold it, but if you're the Pope, certain privileges come with that. Anyway, and then you can see Brother Guy, the top bottom corner, holding the meteorite. Brother Guy is my boss. He's the director of the Vatican Observatory, both in Rome and in Arizona. So he splits his time between Arizona and Rome because we have 2 locations. And there you see Pope Francis talking to Brother Guy right there. So what do? Well, I study stars. So there are about 16 of us who work at the Vatican Observatory, all priests or religious brothers, and each one of us does his scientific research. We work with one another, but we also collaborate. We work with astronomers out there in the world, different universities, different observatories. And so we have those working relationships. We go to scientific conferences, present our results just like any other scientist would, and we also publish in the standard astrophysical journals where scientists publish and all these things. So we do the work of a normal scientist in addition to our priestly work as well. So each one of us has his field of specialization. For the guy, his specialization is basically rock elements in outer space. So if it's a rock, whether it's a planet or whether it's a comet, whether it's an asteroid, whether it's a meteor or meteorite, that's Brother Guy's field of specializations. He can tell you a lot about rocks, big rocks or small rocks in outer space. Brother Bob as well. Father Jonte, one of the Italians amongst our number, he's a cosmologist. So he's the one who can tell you about the Big Bang, about dark matter and dark energy, all these things. the evolution of the universe as a whole, right? Then you have Father D'Souza, who's from India, and he studies galaxies. So he studies how galaxies like the Milky Way form and how they have evolved. And then there's me and a couple of others. We study stars, right? Because if you're a cosmologist, you're worried about how the whole universe acts, right? To you, a star is nothing. So you don't have to know specifics about stars the way that I do, right? But my field is stellar evolution, so I can tell you how stars work in great detail. How stars work as far as we know, right? Stars like the sun, or clusters of stars, right? Groupings of stars, whether it's just a few stars like the top middle, the Pleiades constellation, which you can see during the winter, or even bigger agglomerations of stars, globular clusters, or even galaxies, right? Because galaxies are the ultimate large collection of stars. So once again, I can tell you how stars evolve, how they're born, how they evolve, ultimately what their fate is, right? Does the star have a nice, quiet, natural death like the sun will have? It will become a white dwarf and it'll just flicker out one day. Or if the star is initially more massive, it will go through a completely different sequence of evolutionary events near the end of its life, and it will wind up either a neutron star, very dense star, or if it is even more massive, it becomes a black hole. The sun will never become a black hole, by the way, okay? So we have no need to worry about that. And in particular, what I study are very bright, energetic blue stars that are known as subdwarf B stars, or horizontal branch stars. So in a very old collection of stars like a galaxy, if it's an old galaxy, most of the stars will be emitting a type of light which is red, which red in astronomical terms means it's very cool star. Whereas very young stars are blue stars, and they're very energetic and they have high temperatures. So if you look at that diagram right there, do you see the little spike where it says UV upturn? A galaxy which is very old should not have that, because most of the stars should be old and very cool. But if you see that spike right there, that means that there's something within the galaxy stars that are very energetic and very high temperature. So the question is, well, why do we have those stars? Okay. And it turns out that one possibility is that if you've got a binary star system where you have two stars going around each other, right? One star can attract all the stuff from the other star. And if it happens at a point where the other star has become a red giant, which is what the sun will become one day after about 10 billion years, okay, what it's left with is basically just the core of the star, which is where the thermonuclear reactions are going on. And that's why it's very bright. So that's one theory as to how we get these types of stars, right? If you take a collection of stars, let's say a globular cluster, and you take all the stars and you know the temperatures and how bright each one of these stars are, if you plot the temperature versus the brightness, right? You can actually get a picture of the evolutionary sequence of all the stars in that particular collection, in that particular cluster. So if you see where it says HB, it's flat. That horizontal branch, those are the stars that I study, okay? By the way, the sun would be located where it says MS, main sequence. Anyway, so once again, stars that interact with one another, and on occasion, galaxy evolution. You see the Andromeda galaxy right there. But I also study exoplanets, and that's the project that I'm involved in right now. So an exoplanet is a planet that does not belong to our solar system, right? Okay, these are planets that belong to other solar systems. Exo meaning outside, right? So exoplanets. So part of my work, even though I study stars, deals with exoplanets. And so for the last 15 to 20 years, we've been very fortunate because NASA has launched 2 probes which have discovered thousands of exoplanets revolving around stars in other solar systems, right? That first probe was called Kepler, and it discovered maybe around 5,000 exoplanets. But all these instruments have a limited lifetime, right? You know, to put it colloquially, they run out of batteries, right? It's more technical than that. And so they sent up another probe to replace Kepler, and it's called TESS, Transiting Exoplanet Satellite Survey. And it's the new planet hunting satellite that's in orbit around the Earth. It's very far orbit. So it's continuing on with discovering these exoplanets. So what do I do with regard to exoplanets? Well, actually, we're actually interested in the stars that these exoplanets go around. So here's the thinking. So TESS is up there, and we know TESS is discovering exoplanets, and it still is going to discover even a lot more. So we're collaborating with an astrophysical observatory in Germany, Potsdam. And so the idea is this: we're going to observe a lot of the stars that TESS is observing, right? Banking on the fact that TESS is going to find planets around a lot of those stars. So TESS is only interested in the planets, okay, but we're interested in the stars that go around the planets. We might say, well, Brother Brown, that's apples and oranges, right? How can you be studying exoplanets when you're looking at the star and not a planet like TESS is? All right, keep in mind that TESS finds those planets by what's called a transit. So if you're the Earth looking at a star, or if you're TESS looking at the star, you basically stare at the star, and if you stay staring at it long enough, if the brightness of the star dims for a moment, one possibility is that something that's going around the star has gone between your line of sight and the star, right, to block some of the light out. So those are called transits, planetary transits. And that's how TESS actually discovers those planets and says, oh, there's a dip in the brightness of the star. That means that something probably is going around it. And from that, you can figure out the size of the planet, and maybe its mass and all these other properties, right? So it's actually done by looking at the star. So we're looking at the star as well. And what's our aim? Well, it's all done through light. So take a look at this. You've all seen this. A prism will split white light into its component colors, right? Because, you know, each color of light represents a different frequency of light, right? So if you look and see on the top left-hand corner, that yellow dot represents a star. When something emits light, it emits light across all colors, right? If you split that light into its component colors using something like a prism, or more technically what's called a spectrograph, okay, you get the spectrum, right? You get the rainbow, like you see at the bottom, right? Continuous spectrum. The light runs through the prism, which splits the light up into its component colors, each one of those colors representing a different frequency of light, okay? Just like you have different frequencies of sound, right? Which when you mix all the different frequencies together, what do you get? Noise, right? So you have that. Now, if the light that's leaving the star that ordinarily would give you the rainbow, if that light, which is produced at the center of the star, has to pass through the outer layers of the star, which are cooler than the center, then what's going to happen is that elements that are in those outer layers of the star at cooler temperatures will absorb some of the particles of light, right? Some of the photons. And each photon corresponds to a different frequency color of light. So instead of getting the rainbow, look at what you get on the top right-hand corner. You get the rainbow, but a few dark lines, right? You see that? So those dark lines represent colors, frequencies of light that were eaten up by the various chemical elements that are in the outer atmosphere of the star. Carbon and nitrogen and oxygen, right? And so if you look at the spectrum of the sun, that's actually what it looks like. You see all the dark little lines right there? That allows you to see what kind of elements are actually present inside the sun. So if you use that to get a plot, you look at the colored part and you see where every dark line is. If you graph the intensity of those dark lines, you can get a graph like what's above those, right? Where you see the little dips in the curve, right? Each one of those dips corresponds to one of those black lines. And so those little dips, you can actually go one by one and identify them and say, oh, that little dip is due to hydrogen gas. Because we're able to determine that in the laboratory. You heat hydrogen up and it gives you these lines and you go, okay, that corresponds to that frequency. So what we do in the laboratory here on Earth can help us examine a spectrum of a star and figure out what elements are there just by looking at the dips. So you look at the top left. Each one of those dips corresponds to an element that ate up a photon, or the bottom, it's an even higher frequency resolution. In other words, that bottom diagram, it was an instrument that was able to split light up into such fine detail, okay? The instrument that was used to get you that on the bottom costs how much? $10 million. Okay, it's not ours. We're using it from somebody else. It belongs to the Germans, and I'll explain that in a second. And so you get a high resolution spectrograph, which gives you great detail in terms of being able to tell what a star is made up out of. And so if you want to look at the spectrum of the sun, you see all those black lines? It's incredible. And each one of those lines corresponds to a particular chemical element or molecules that have absorbed some of the photons that are being produced in the center of the sun, and they're trying to make their way out. Okay? So if you look, for example, on the the bottom left, you see that dip right there. That's due to hydrogen. We know that. You see the middle one, okay? Those are lines formed by calcium. Calcium, which is present in the outer surface of the sun, okay? Outer photosphere of the sun. If you look all the way on the bottom right, you see those three little lines? We know that those are due to oxygen being present in that outer photosphere of the sun, right? So that's how you can tell what these stars are made up out of, right? Which, by the way, stars are mostly made up out of hydrogen, right? Hydrogen and then helium, okay, but especially hydrogen, and then trace amounts of these elements, which from the point of view of the star is almost nothing, but that's more than enough to form a huge number of planets with an oxygen atmosphere, right? And nitrogen and all these things. So, what's the connection? If you look at this picture on the left, that's actually a real picture that was taken by the ALMA Observatory in Chile of a solar system that is being born, okay? So what happens? Every solar system, including ours, so goes the theory, okay, began as a huge cloud of hydrogen gas, mostly hydrogen, a little bit of helium and some other elements that were produced by other stars that had been there before and then blew themselves up, had produced all these elements inside, and it spewed all that stuff out. Still mostly hydrogen, but now you get oxygen and nitrogen and carbon. And what happens? That cloud recondenses because of gravity, right? The clumpiest part becomes the star, okay, because stars are far more massive than their planets. Okay, so you see the very center of that's a star being born right there, okay? And then do you see those little black rings that go around? Those are planets that are being born. So what's happening is that you've got other little clumps that are going around the bigger clump, which is going to be the star. And those little clumps, as they go around, okay, they're eating up all the material as they go around. They're recreating the material from that cloud onto themselves, okay? Which is why you see those sort of dark lanes right there. So you see a solar system being born, okay? And so, what's the connection between the stars and the planets? Well, take a look at this. In general, okay, the planets and the star that they go around are formed from the same stuff. So the thinking is, if you know what the star is made up out of, you can at least make a general prediction what the planets might be like as well, right? Obviously, you can't do it in great precision, right? But at least you can get a general idea, and vice versa, whatever that. So we're studying the chemistry of a star, trying to see what it's made up out of, but we can be able to predict and say, oh, okay, it might have planets like this. So if you have, a star that has an unusually high amount of magnesium and silicon and calcium and all these things, okay, titanium and iron, these are all elements that form rocks in one way or another, right? Which is, you'll get a rocky planet, right? As opposed to the gaseous planets like what? Saturn and Jupiter, right? Which have no surface. Okay, so you can at least make those types of generalized predictions, right? Anyway, so it's not apples and oranges. There actually is a relation, right? So the work that I do, I look at the lines of a spectrum. That's a screenshot of something that I work with. And you see me, I'm looking at the oxygen lines and measuring them and from measuring the oxygen lines, I can then get an idea of how much oxygen is present in the surface of the star, right? Anyway, those are pictures of our work with regard to exoplanets and observing these stars. So as I said, we're doing this in collaboration with a German observatory. So the two other telescopes that are on the mountaintop with us, if you see the one all the way in the back, that thing is about 20 stories tall. It cost about $250 million to make. and it's owned by a bunch of different countries. Half of it is US owned and 25% German, 25% Italian, roughly. And so what happened was that the idea on the part of some of the Germans was, why not connect our beautiful spectrograph, which is in that gigantic telescope, which can give you all those great detailed lines, right? Why not connect that to your telescope, the Vatican telescope, because we can give a lot of nights to observe, right? It's very hard to get observing time. But since we own our telescope, our own telescope, okay, we can devote as many nights. And so that's the working together. So they hooked up giant $10 million instrument on that giant telescope to our telescope. And so if you look at that center picture, you can see the instrument, or at least the attachment with the wire. And so those are just pictures right there of us working in the control room and all those things. Anyway, the last part of the presentation, I'll just take 5 minutes and then we'll do questions. Astronomy is fun, right? So look, the universe is a big place. And it's just so much fun, so many wonderful questions. Why exoplanets? Why is that such an interesting thing? Well, one of the big questions that we're trying to find out, right, is, are there others out there, right, in this big universe, right? Are we alone, or are there others? And of course, if there are others, where are you going to find them? Probably on planets, right? Other planets out there. Which is why we want to do exoplanets. There's other reasons, obviously, to study exoplanets, right? There might be future homes for human beings in future years, right? So space is big. So once again, let's go on a quick journey, right? Let's start out with the Earth and our beautiful planet, which is special, at least in our part of the universe anyway, because it's teeming with life. Okay, and then you look at the Earth from above. That's one of the astronauts on the in the International Space Station. Okay, then this picture was taken of the Earth and its moon as one of the probes being shot into outer space was leaving. They just turned it back and they said, "Why don't we take a picture of the Earth and the moon?" That's an astounding thing when you really consider that, right? We know that we've sent a lot of probes to Mars, right? Our rovers and also other probes that are orbiting Mars. One of the probes on the surface actually took a picture on Mars, the surface of Mars, of what a sunset looks like from Mars, right? We're all used to looking at the sunset here from Earth, but what would it be like to be on the planet Mars and actually see the sunset? Okay, that's a picture, that's a real picture, okay? That's the Martian sky, all right? And then we know that we have all these planets in our solar system, right? And so, we have Mercury, and of course the Earth, Mars, Jupiter, and then Saturn, Uranus, Neptune, and of course the highly debated Pluto, right, which is known as a dwarf planet or trans-Neptunian object. All right. Obviously, we know more about Pluto than this top-bottom photograph says, because the New Horizons spacecraft passed by there a couple of years ago and gave us all these wonderful pictures. You look at all the stars in our neighborhood. We're in the center, Sol. Okay, that's just a convenient diagram, but these are all our stellar neighbors, stars around us, and stars that might have planets around them, right? Other different solar systems. The one that's closest to us is Proxima Centauri. Sometimes you hear Alpha Centauri. Why do those two get named as the closest? Because you sit there and you go, well, what gives? One of them's got to be closer than the other, right? And you sit there and you go, actually, it's a triple star system. It's a solar system with 3 stars instead of 1. Which, by the way, the sun is in the minority. Most of the solar systems in the universe, we think, okay, have multiple stars in them, okay? More than half. Okay? Anyway, so that's our solar neighborhood right over here. You pan out and you start moving out of the solar system, and in our neighborhood, you see all these wonderful clouds of gas, these nebulae. Some of them are the result of stars that blew themselves up in an explosion at the end of their life, like a supernova, like these pictures right over here. We've got black holes, right, that we run into, stars that have died and collapsed under their own mass, because they're very massive. So these are all examples. The top left is a schematic diagram. That's an artistic representation, but you see all those other pictures? Those are real, okay? Usually the black hole is hidden under all that gas, right? All the other pictures, and of course, that top right-hand picture is the very first picture of a black hole that was taken by astronomers just about 2 or 3 years ago, maybe 4 years ago. Okay? Okay, that's a real picture of a black hole. Now, keep in mind, you actually cannot see the black hole. Okay? Why? Because the black hole absorbs light, right? And everything that we know about the universe is based on the light of objects that are out there coming to our telescopes, right? So if a black hole eats its light and it never gets to us, how can we see one, right? Well, what's happening is that the light that is outside the event horizon, the event horizon is the point of no return for the black hole, right? As long as you stay outside the event horizon, you can still escape, even albeit with great difficulty. So once you fall inside the event horizon, you'll never leave. So the light that's surrounding the black hole, that's light that has managed to leave the black hole because it's outside of the event horizon. And hence you see the dark spot inside. That's the black hole. But we know it because, I mean, technically we can't see it, but we can see it's a fact, right? Anyway, I study clusters of stars. So these are globular clusters. These are collections of 1 million to 10 million stars. You can see how dense it is. And once again, we keep panning out. But over here in our part of the solar system and our part of the galaxy, and we find out that we're only one of the little arms of our galaxy, the Milky Way, right? So we are right there, kind of that central arm. And we pan out even more, and you can see where it says sun's location. That's where we are. The galaxy, our galaxy has a couple of 100 billion to almost 1 trillion stars, the Milky Way galaxy. And that's a nice picture of it right there, as seen from the Earth, right? I'll get back to that in a second. Pictures of the galaxy. Once again, they say it's a spiral galaxy, right? Like a giant hurricane in outer space. And then these are some of our neighbors, right? The galaxy that's closest to us, which is M31, the Andromeda galaxy, different pictures of it right over here. Another trillion stars there. It's even bigger than our own galaxy, they say. Or the Whirlpool galaxy, right? A beautiful spiral galaxy. It's like our own. And so, boom, you just keep panning out and you see all these galaxies and how big space is, right? And you see, once again, just pictures of different galaxies. And once again, our galaxy, along with the Andromeda galaxy, is a part of a local group of galaxies. But here, you can see even other groups that are close, right? And so you pan out even more, and it turns out that you just see more and more galaxies. And we're just at a point right there in that bigger supercluster of galaxies, okay? And then boom, it just goes on and on. Each one of these, is a galaxy, and you pan out even more, okay? Those are clusters of galaxies in the universe. And so once again, take a look at that. I mean, just the amount of galaxies that you see in a picture taken like that by one of the surveys. This was the result of a survey done by the Sloan Digital Satellite Survey. But once again, it's pictures. They're trying to get a map of our universe, okay? And so, boom, it just goes on and on. That's the picture of our universe, microwave. That's the cosmic background microwave radiation, the afterglow of the Big Bang. I'll put it down so you can see that. And I thought that the universe evolved like that. The Big Bang, and then the more you go back, you're forward in time, it gives us our universe. So we'd be at the bigger end of the cone. Anyway, and for all of that, everything that we've ever seen with our telescopes, they say, is only about 5% we think the universe is, because 95% of the universe consists or exists in a form that we are not able to detect, okay? Because it does not emit light. And so how do we know about things in the universe? Because of the light that comes. Now we have gravity, right? Because we have these LIGO detectors which are able to detect gravitational waves, which are formed by very cataclysmic events like black holes colliding, right? So hopefully that can tell us more. Okay? To study the universe, not just its light, but also its gravity waves. But at the moment, we don't know what 95% of the universe looks like that they say is there, okay? It's in the form of dark matter and then dark energy, okay? And so these are simulations. The light part that you see there, that's luminous matter. And then all the purple stuff, they say that's dark matter. The luminous matter is where galaxies are forming in stars, okay? And then they say that, in turn, our universe, 95% of which we don't know anything about, may be one universe amongst an infinity of universes called the multiverse. We're not sure about that. That's just a theory, but who knows, right?